Log on, tune in, find out. Another good idea from Cambridge.
And the title of the talk is to estimate or to predict implications on the design for linear mixed models. So as I understand, you will talk about small samples we are all interested in, and we are looking forward to a talk. Okay.
Thank you. Thank you to the organizers for inviting me and for being back here again. Well, a little bit disorganized. When the organizers asked me to give a talk, I was a little bit curious. Where is it? Yeah.
This one?
Okay, looks perfect.
This is you?
In my younger days. No, this is, thanks for the hint, this is the names-giving person of our university, Otto-von-Guericke, which was one of the last famous scientists of our city. He is, probably you know him, he's the inventor of the nothing, person with the Magdeburg half-balls, the vacuum. And occasionally it happened that he became a co-author of mine on a conference, so which made me very proud. So this is the official outfit of our university now. So I have to show it once and at the end once again. But turn to what is my usual outfit. Okay, when I was asked to give a talk here, I said, okay, non-linear or maybe generalized linear is a little bit hard for me. So I still have to struggle with the linear problems. And I leave the non-linear things to my young students. And occasionally it had happened that we had some money left from a project from the German Federal Ministry of Education and Research, the BMBF, which has a funny name which sounds like some Swedish furniture from a big company, Schwabe. And I had a young lady working in this project, and I was thinking, what could we did, what might be interesting? And this is Marina Bruce, who is in the audience, and she did all the work, and I just tried to harvest the whatever to get out. So the title is a little bit provocative, to estimate or to predict. We will see that it makes a difference what we want to do, and the background is that I have been working with pharmaceutical industries and with pharmacists, and they told me, okay, we want to individualize medical applications, just to fit the dosage to a person and not just to say what is a typical dosage or what is a typical treatment. And that's what it is about, and that the design might look different. So when I started with this topic, or even years before, I always heard the comment, oh, everything had been done. There's a seminal paper by Kladitz and Pilz in the early 80s and of the last century, of the last millennium, and you can find everything in there. And I was a little bit discouraged when we started, but we had to spend this money, and so I asked Marina to at least to resemble what had been done about 30 years ago. And then I noticed that things look a little bit different than we expected. In particular, that these Bayesian designs, which were mentioned at that time, may be completely misleading and maybe quite useless for these problems. So, okay. So, what I'm going to talk about today is, again, something like a drama or tragedy in 5 acts with a prologue. The prologue is a short introduction where I want to introduce a model and want to show that I know, at least can draw a nonlinear curve. Then I will give some hints on the model description, just to introduce notations. The main part of the talk will be what I was thinking about estimation and predictions in the quotation marks, because it is this kind of prediction for the individuals involved in the study, not for the future. So it is some kind of estimation for the individuals. We'll say something about optimal design, which is not so much, and I will give a simple example which shows that considering estimation or prediction makes a difference, and then some outlook as every time that there are still things to do, fortunately. Well, so start with a short introduction. So what are we interested in? So we had this project of pharmacokinetics, and one might be interested in the concentration of of a drug in someone's blood, and you have seen this curve already this morning, at least the formula for this curve. So it looks like that, and we might be interested in finding out the correct parameters or to find out the correct curve. So, and what we have at hand is we cannot observe the curve or exact values. We have noisy observations, which are the values of the curve evaluated at certain time points or at certain settings, plus some additional noise. And from these observations, there are a couple of them, we want to estimate the whole curve or some characteristics of that. So today I will lay most emphasis on estimating the whole curve, but all our objectives might lead to similar results. Okay, and what means design? Design means, or optimal designs, to find the best time points, best settings to get the most reliable or most precise estimate of the curve. Okay, so far nothing new. Well, but the problem is, as I mentioned in the beginning, and as we heard in the first talk this morning, there might be some differences between individuals. So we have a couple of people there, and they all get the same drug, and they behave different. So they all have this elimination curve, which has the same formal structure, but with different parameters. And there are two questions which arise. One question is, what is a typical curve, which belongs to some kind of population parameter? How does a typical individual react on the treatment? And the other thing is the individualized question, how does a certain person react on the treatment? So we might be either interested in estimating the typical curve or in estimating or predicting, because these are some latent variables, as we have heard this morning, for the individual curves of each person at hand. Not in the future, but of these which are involved in the study. Okay, so first to start, the model description, what we will do, I will here forget everything about nonlinearity, but I'm quite sure that all these problems or all these differences will not vanish if things become nonlinear. By my experience and my credo is every problem in linear models will come back in nonlinear, will not disappear. So okay, we have a linear model, which means linear in the parameters. We have observations, let's say n of them. We have some explanatory variables which we can adjust. This is a design. And we have some random errors which are independent, uncorrelated, homoscedastic. Keep things as simple as possible. So I don't want to make the things general. I want to keep boil it down. And we know the regression functions. What we don't know and what we're interested in are the parameters beta 1 to beta p. Or in fact, we are interested in the mean response mu of t to estimate that. Cool. But again, just to stress once more, if we have different individuals, we will have different curves. So now we have linear models. So in fact, the simple example at the very end we will consider just simple straight line regression. And just to imagine what kind of individuals these are could be. These are need not be human beings. It can be animals like these little nice little degus. Probably most of you know what's going on with them. So so our neuroscientists use them for making a model of the human brain, because they believe that the behavior of these nice little South American rats is similar to that of human beings, in particular with respect to whether the fathers are involved in the education of the kids. And so they want to find out what happens if they put out their father from the family or not. But fortunately or unfortunately, the results are rather ambiguous. Okay, but we have data from these animals and want to find out what's going on with them. And what is most important, the individual responses follow a common model. Here in this case, simple straight line regression, or as in the introduction, this elimination curve. Well, so this makes a difference. So we have a hierarchical modeling, everything mentioned this morning. I have these two indices which were criticized, but I think two is enough. 3 or 4 this is not so good. So Yij, this is a J replication or J observation at individual I, and we have this response function transpose a linear model with the parameters, but now the parameters depend on the individual. These are some beta i's, giving, for example, for the straight line regression, this is a particular slope and a particular intercept. And for simplicity, I also assume normality of the error terms and normality of these random effects of the individual. So these are not fixed effects we are interested in, these are random effects. But as I will only consider best linear unbiased estimators and predictors, we could break these things down just to moment assumptions. Okay, and we are either interested in the population parameters or in the individual parameters. And throughout the remainder of the talk, population parameters will be denoted in blue, and the individual parameters will be related to red. Hopefully you can distinguish that. Okay, well, if we have just to do some modeling, if we can subsume all observations of one individual in one vector, and then we get a model equation saying that the observational vector of individual I is some individual design matrix Fi times the individual parameter, and we can split up the individual parameter commonly in individual effect and the population parameter. So the BI is the individual effect, which has 0 mean, and is the difference between beta I and beta. So, okay, nothing has happened. This is just rewriting these things to make computations easier. Well, okay, so if you have this notation, we can quickly find out the individual covariance. We have seen this formula already this morning, so I could have skipped half of my transparencies. But just to see that we have some correlations within the observations. So the covariance is And I have also done the same trick to get the sigma square out. So we have some the covariance structure which is the identity matrix over there, which is related to the random errors, and this FDF transpose, which is related to the effect of the individual parameters. And for example, in the very simple model, if you have a random intercept or random block effect, this will result in equal correlations between all observations. So things simplify quite dramatically then. Well, okay. And I even simplify things more because I'm too lazy. So I assume that all individuals are treated the same way, that we have the same number of observations per individual, and we have the same experimental setting per individual. So this results that we have the same individual design matrix for each individual, and consequently the same covariance matrix for each individual. And this gives us a representation of the full observational vector if we stack all individual observations upon each other in this fancy Kronecker product notation. So where this one n denotes a vector of length n with all entries equal to 1, and the in is, as all, usually the identity matrix. And the covariance matrix factorizes according to this Kronecker product structure. So this makes life terribly easy. In particular, if we look for estimation and prediction. Whether these single group designs are good or not, this might be still a question. Whether they are can be used is even, or can be applied, is even more difficult problem, as in particular in pharmaceutical applications, in oncology, you might be faced in situations where you have only 1 or 2 observations per individual, and if you have more parameters, you cannot do that. But I assume we are in the most nice situation where we are able to do a couple of observations, not very few, but also not very many. Let's say 10 or 5 within one individual. Okay, so what is the difference between estimation? We either want to describe the typical curve, which is this typical straight line, with the population parameters, population intercept and population slope, which are the means of the individual parameters, or we are interested in the individual curves themselves. See the up and down, hopefully see the blue and red distinctions. And we might be interested either in the population parameter beta in the estimation case, or in the prediction of the individual effects bi, or the individual parameters beta I, or in particular what I'm will insist on in the individual response function mu I. Well, okay, estimation. So you can fall asleep for at least one slide. If you do the best linear unbiased estimator in this very simple design model, you will find out that you can use the ordinary least squares estimator because everything is interchangeable, and in particular the estimate of the population parameter is nothing else than the ordinary least squares estimate based on the mean of across all individuals. So this is one possible representation. And the nice thing is this can be done independent of the knowledge of the dispersion matrix D, which gives the ratios of the variance of the individual parameters compared to the error variance. But Empire Strikes Back, the D will come back again later on. And the best linear unbiased estimator of the response function is then given as a linear transformation F transpose beta hat. So this is nothing special. So what about yes, so here the D is back again in the covariance structure. So the covariance of the estimator is just the, don't look at the formula, it is just the an average, in a way, of the variance covariance function in the model without random effects, the F transpose F inverse, if everything is regular, and additionally plus the dispersion matrix D. Okay, and this will be quite helpful later on for design, at least for the design problem I'm interested in. So prediction. So if you use Henderson's mixed model equations, you get the best linear unbiased predictor of the individual effects BI hat, which is this Bayesian information matrix if F transpose F plus D to the minus 1, and the inverse of that times F transpose, and then the difference of the individual observations to the mean of the observations. This nice form only occurs for this very particular design, of course. But as we have the design at hand, we can do it. But this only works if the dispersion matrix has full rank. It's a regular matrix. The problem has been addressed already this morning, as far as I remember. Okay, and then the predictor of the individual parameter we can get as a sum of the estimate for the population parameter plus the individual effect, which results in some weighted average of the estimator based only on the data of the corresponding individual and the population parameter. Well, and then we can get a predictor of the response function. Well, so now we don't have to look for the variances of the predictors, but for the mean squared error. So the deviations from the true parameters. And if we calculate, we get this nice and fancy formula. And we see that this is again a weighted average of two things. One is a good colleague of us, which is a covariance matrix in the model without random intereffect, and we get this fancy Bayesian covariance matrix down there, F transpose F plus D to the minus 1 inverse. And you see this depends on the number of parameters, so the larger the number n of individuals will become the influence of the Bayesian covariance matrix will increase, but the standard covariance matrix of the model without random effects will not disappear. This is an essential fact to observe. Well, okay. So what about this Gladitz-Pilz business, which I mentioned in the beginning? That we only have to look for this Bayesian covariance matrix. That's the solution. If we know the population parameter, beta, then we have this Bayesian solution. Then this is the first misprint, I see. We have, no, it's okay. So we can estimate the individual parameters and the corresponding mean square error then boils down to the Bayesian covariance matrix. Well, good news and bad news. So, why can we use that or not? So the good news is this is not the true thing. The bad news are things become more difficult. And one thing is if we have a finite number of observations, we always have a finite number of observations, we cannot neglect this additional term. And the second thing is this only works if D is regular. So then one might try for general dispersion matrices, and if you do some matrix computations, you can find out, you can solve these things, and you get some strange formula for the predictor of the individual parameters. Don't want to go into detail for that, and we get some mean squared error, which is again an average of our old colleague from the fixed effect case and something else, which can either be written like that or like the term up there, but which cannot be properly interpreted, but it can be calculated for even for singular dispersion matrix D. In the case of regular D, it reduces to the representation we have seen before. Well, okay. So this is the basement on which we can now do our optimal design, and essentially this was the hard work. Now comes the easy work, just computational work. So what optimal design is, I will just stress on exact designs at the moment. So we have to find n settings such that the corresponding covariance matrix or the variance of the response function is minimized in some sense, either estimation or prediction sense, blue one or red one. And I will stress today, and this is my favorite criterion, the integrated mean square error criterion. If I want to estimate the function, I look for the mean squared error or the L2 distance, and then integrate everything out. And if you do that, so the integral of the mean square error over the sign region, you might get a linear criterion. It's a trace of the covariance matrix of the parameter vector times some other nice positive definite or positive semi-definite matrix. You can do this in the estimation case. In the prediction case, you additionally have to sum up the mean square errors for all individuals, but in fact it makes no big difference. Just plug in what you have. Okay, so for estimation, again, as you might guess or might remember, everything is easy. If you have a linear criterion, then like the integrated mean square error, then this decomposes additively in something which depends on the design and something which depends on the dispersion matrix. So we can forget about the second term because it is constant. We are back in the situation that we can use the optimal design for the for estimation in the model without random effects. So this is somewhat boring, but things become different if we want to predict the individual parameters. So this is again linear, but and it decomposes into two terms, and one of them is again what we know from the model without random effects, but then we have additionally the Bayesian integrated mean square error in case that the matrix D is regular. Otherwise, we have a little bit more complicated representation, but this is no additional big problem. And therefore, we now have two terms which we have to optimize simultaneously, in a sense. So we have to optimize this weighted average of these two criteria. It's not so difficult, but we have the main difference to the Bayesian approach is that we still have a very small amount, 1 over n, of the for the estimation of the population parameters in there. So the second term. Okay, so easy case, random intercept. Then everything somehow disappears. The first term reduces to a constant, and only the second term related to the model without random intercepts remains. So we can find out that the optimal design does not depend on the dispersion matrix, and we can just take what we are used to take. So that this is not true in general. This should give the small example at the very end. And we have the simple linear regression on the interval 0, 1. And we assume additionally that the intercept and the slopes are independent. And then you get some curves, and usually I put some guinea pigs over there. But after reading the menu of Thursday, I put some guinea fowls over there. I was a little bit anxious, so I looked it up. And well, and and if you want to find the optimal designs in this case, we have to have this very simple information matches over there, and we have to optimize this little bit more complicated criteria. We did this numerically, or for the estimation it's clear this can be done by hard calculation. That it's easy to say that you have put half of the observation at the two endpoints to estimate the curve the best way with minimal integrated mean square error. But if you want to predict, then this depends on the number of observations. If the number of observations gets large, and if the variation of the intercept is small and of the slope is large, you should put a very large amount, or the majority of the observations, at the right endpoint, where the curves are varying most, where it is difficult to observe. Here you have the corresponding weights. So this is, of course, you should discretize that. This is a case of 100 individuals, which is not small, and of 10 replications per individual, but it's just a nice curve, which gives a strong impression that the weights go up from half of the observations at both endpoints to approximately 90%. So this means with 10 observations, 9 observations at the right endpoint and 1 observation at the baseline. So what in fact would the base optimal design do in this case? This is not a 1 million question. 1 million pound maybe, okay, should over half a pound, because it's so easy. The Bayesian optimal design says put all observations at the right endpoint. But this has some small disadvantage. You can't estimate the population parameter. And and the efficiency will go dramatically down, while this criterion prevents from going to 0. So or to 1. So it goes close to the extreme values, but it says you have always leave at least one of the observations at the baseline. Well, okay. Small comment on the efficiencies. Is it worthwhile? So if we use the equireplicated design, it's a naive design coming from the estimation problem, and we increase the variance of the slope. I just plotted this ratio because then it is bounded between 0 and 1. Then the efficiency, which is the ratio of the integrated mean square errors, decreases to about 60%. So this means you need about what does it mean? You need about 60–70% more observations to get the same precision. Well, and if you use a Bayesian optimal design, as I mentioned already, this has 0 efficiency because you can't estimate anything. So therefore, one has to be a little bit careful about these things. Well, outlook, always open problems. Yeah, the optimal designs depend on the dispersion matrix, as you might have noticed. So, and usually this is not known. So therefore, one has to, if you choose the wrong one, this may badly perform. Talks down to 60%, or even worse. So one might think about the average criteria, pseudo-Bayesian, whatever, or the minimax criterion. Still work to do. Other criteria seem to be, by our experience, more sensitive to the specification of the covariance matrix of the individual parameters. The fourth item, I can't remember what I wanted to say. Prediction of individual, okay, the prediction of individual effects, BI, not of the individual parameters. These share the problem with the Bayesian design that they may result in singular designs, as far as I remember. Do I remember properly? Well, and then just to come back to the topic of the workshop of this week, I really don't know at the moment the implications on nonlinear response, but I'm sure that this difference between estimation and prediction does not disappear if you are nonlinear instead of linear, and you can do anything else. So thank you for your attention.
Questions?
What are the computational implications of your criterion, the IMSE? Is it straightforward?
I did it in 3 lines in R. Just by searching on a grid, because the function is really smooth. So the position is about 1,000 whatever. So I don't care about the error I do then. Sorry, not very sophisticated.
You alluded to the minimax criterion. Any results you have on that?
Not yet, not yet. I just
So you
want to mention that one should do that.
So you will maximize over all the possible values of the parameters in
Yeah.
the dispersion matrix?
Yes, or I would maximize over or minimize over the efficiencies. So I would prefer the maximum efficiency criterion, just to standardize with respect to the best possible to do, not just looking for the worst case. But anything can be done, just to make things a little bit more robust.
Yes, please.
It's just a comment more than anything, but a student and I worked on this sort of thing for a while. Something that we had to wrap our minds around was if you change the location of time, instead of counting from day 0, you count from day 1, and then of course your matrix D changes.
Yeah.
And
Yeah.
how do you, what happens to the optimal designs, Rainer?
This will definitely change.
Yeah.
Yeah. In fact, for these situations, if I manage that so if I change the design region, then this will introduce additional covariances between the parameters. So I assume that they are that the slope and the intercept are independent. This will be no longer true if I transform it. So if I, for example, would have considered the symmetric design region from -1 to +1, and the diagonal dispersion matrix, so independent intercept and independent slope, then the optimal design would always be that one giving half observations to the right and half observations to half observation to the right and half to the left. because everything is symmetric. But this is the easy thing. It's not so interesting. So of course, you can cope with that. You can always transform it back to 0, 1 or to -1, +1, but you will always get a different dispersion matrix or different structure of the dispersion matrix. But thank you for the hint.
Sometimes you want to do both estimation and prediction because you want. So did you think about any combined criteria, or is it then the prediction would be back to the Bayesian criteria? I was thinking.
No, you will never go back to the Bayesian criterion because then it might happen that you cannot estimate anything.
Yes, but if you combine them together.
Yeah, you can probably. I guess you could consider any weighted average of the prediction and the estimation, or product, or whatever, any meaningful combination. So I think this should be straightforward.
I've run into a conceptual difficulty thinking about the individual parameter and characterizing variability in that. And I was wondering if you were already in a Bayesian point of view, because to me, when I think of the sampling theory point of view, the beta is a parameter, but BI is a random variable, and I can't actually think of what the combination to get a beta I would be.
Well, I think this is a philosophical problem too, where you consider the beta I or the individual curves as individual parameters in a Bayesian sense, or where you consider them. So I'm not a Bayesian, definitely not. But, I think it is appealing to assume that individuals are coming from a huge population, and so they should be characterized by by individual random parameters coming from the big distribution, and then whether I consider this as an outcome of some Bayesian thinking, or whether this is an outcome of some sampling scheme, by my opinion, doesn't matter for the inference. It matters for how you want to interpret it, whether you call it prediction or estimation or whatever you might call it. So in a way, it is a Bayesian estimation of the individual parameters. Therefore, also it is clear that this Bayesian covariance somehow occurs. But it's not only this Bayesian covariance. There's additional, the additional thing is we don't have the knowledge on the population parameters. In the Bayesian context, we usually assume that we know that the population parameters. So this makes a slight difference, and this makes a difference between the approaches and the criteria.
I have a sort of a comment or question. In practice, we do sort of adaptive design. We estimate the value G, then look at optimal design, add this optimal design to the rest of the data, re-estimate D, and go alternating between optimal design and D. And then I draw your attention, and you said things are complicated. And things are complicated simply because the covariance of fixed parameters are derived for D fixed. So now D is not fixed. D is a random variable, is an estimator. So even before going into optimal design issue, we have to reconsider the entire theory of mixed effects because we are talking about small sample issues. Agree?
Yes. I was a little bit tricky in not mentioning explicitly that I assume that we know D. So I didn't care about how to find out, of course, that D is fixed. So for the estimator, if you look at it is not involved, but in the prediction it is involved. So true. So therefore, adaptive would be a good approach. So I should have mentioned that, but I was too much in a hurry to prepare my transparencies.
We can leave this as an open problem number 1, right?
At least.
More questions? Yes, ma'am.
Ronnie, can you comment a little bit more about selection of number of observations? And wait a second, I didn't finish. I started to laugh. You see, in traditional experimental design theory, nobody cared about number of observations because continuous design do not depend upon. So you know all this stuff. But in this case, we have actually two numbers of observation. First, it's for individual, and the second, how many individuals. So very often people address it introducing costs. So can you comment what you have, how to select it optimally? So did you think about it?
The answer to the second last question is yes.
For how long?
The answer to the other questions is that in this context, I was not so far. We are still under progress, hopefully. But there's another PhD student of mine, Prof. Reis, working on the optimal allocation if you want to estimate the random coefficients. And I'm not quite sure whether this is so dramatic for the location parameters, for the variance parameters. It is a big problem. For the population parameters,
It's a problem as
yeah,
well.
it is a problem as well. So I would guess, but this is just a claim that one should have. If there were no recrusion costs, then we should have very few observations per individual, but not too few, because otherwise we cannot estimate. If we assume equal regimes, equal designs for each individual. But I think this is a good hint for our research.
I guess one last question because we're out of time.
So, integrated mean squared area, you might be more interested in some regions than others. You might be interested in regions outside your region of experimentation. Have you played around with the weighting and also the area of integration?
Well, no. It is not, from the theoretical point of view, it's no problem, because we just plug it in. And in fact, I did the calculations the last 2 days. So, and I had no actual good reasons from the practitioner to say, oh, I would be interested in this particular region. But for example, extrapolation would be a very interesting thing to do. So what to do?
This Chebyshev theory of extrapolation.
Yes. So I think this would be a good thing to do in future. So this is not, by no means complete. And as I told you in the beginning, I was not sure whether not everything has been known already for 50 years. I was waiting for Valerie to mention that.
Okay, thank you very much.